This is section 1.3, writing definitions. So this introductory slide actually is a little activity to determine what or who are widgets. So in the top left of the screen, we have some examples of widgets. On the top right of the screen, we have some examples of figures that are not widgets. And our job is to determine in the bottom middle of the screen which of these is a widget, A, B, C, or D. Now, if you're watching this at home, you should pause the video for a minute and think about this. Take a look at the widgets, not the widgets, and determine what is a widget, and then choose A, B, C, or D, or maybe more than one. So let's categorize and explain what a widget appears to be. So it's some sort of figure. It certainly appears that the inside of that figure is always some color other than white or black. So like that's green and purple and blue and like kind of like a red. It looks like each of these widgets has some sort of tentacle, and each one has an eyeball and a claw. An eyeball and a claw, an eyeball and a claw, an eyeball and a claw. Okay, so we kind of categorize it as that. Another characteristic, it doesn't have anything inside of it except for that color, no shapes or anything. All right, so let's go over to the examples of things that are not widgets. So this is colored white, so that would mean it's not a widget, because even though it has an eyeball and a claw. Let's see. This is not a widget because it has two claws, no eyeball. This is not a widget because it has two claws and an eyeball. None of the widgets had three tentacles. And this one has a color, it has an eyeball, it has a claw, but notice it has some shapes inside of it, a triangle and a circle. So that must be what's making it not a widget. All right, so we kind of know what widgets are and not widgets, and now let's determine down below. Let's look at A. A is colored green, it has an eyeball, and it has a claw. That certainly appears to be a widget. How about B? B is colored inside. It has a claw, but it actually has two claws, no eyeball. So I would say that's not a widget. So let's put an X through that one. C? Oh, C has a triangle inside of it, so we know right away that's not a widget. And D has three tentacles, so we know that's not a widget. So A is our only widget. Now you may be asking yourself, well, why are we doing this? And the answer is because we are learning to write good definitions. And this is extremely important in geometry, in math, and really in life. I often tell students, say what you mean, right? You can't write something down on a homework assignment or on a test and turn it in and have it marked wrong and then come back later and say, well, what I meant was, because what you write down has to be what you meant, right? You have to choose your words carefully. So this activity is kind of a nice introduction into what we're talking about in this section. So how do we create a good definition? Well, there are actually 3 steps to creating a good definition. Step 1, classify your term. Step 2, differentiate your term from every other term in that class. And step 3, test your definition by trying to find a counterexample. And if you think back to our widget example, we kind of did these 3 steps, right? We classified them as figures. We differentiated the widgets and the not the widgets. And then we tested the definitions with A, B, C, and D by seeing which ones were counterexamples. All right, well, here's another example. Everyone knows a square is a figure with 4 equal sides. Yeah, sure. Or maybe not. What's wrong with this definition? Well, what's wrong with it is we can come up with some counterexamples. If you're watching this at home, pause the video. Try to picture a counterexample. A counterexample that abides by the definition, a square is a figure with 4 equal sides, but it's not actually a square. When you're done thinking, hit play again. Here are actually 3 counterexamples to that definition. Let's look at the first one. This first one, yeah, that's certainly a figure with 4 equal sides, but definitely not a square. How about the second one? Well, yeah, that's a figure with 4 equal sides. In fact, it has 5 equal sides. So it abides by the definition above, but it's definitely not a square. And then this one over here, also a figure with 4 equal sides. It just happens to have a whole lot of other sides as well. So again, it abides by the definition above, but is definitely not a square. So how can we make a definition of a square better? Again, if you're watching this at home, pause it and think of your own definition of a square. How would you make the definition above better? A square is a 4-sided figure that has all sides congruent and all angles measuring 90 degrees. This definition is much more complete than the one above. The key thing that was missing from the definition above is that the 4 angles of the figure have to be 90 degrees. They have to be congruent. In addition, we have to categorize a square as a 4-sided figure. Here are a couple more definitions. Parallel lines. Lines in the same plane that never intersect. Perpendicular lines. Lines that intersect at 90-degree angles. Let's analyze these definitions before moving on. The definition of parallel lines seems pretty straightforward, right? 2 lines that never intersect. Well, be careful, because there's a key phrase in here that you must have in the definition. In the same plane, right? 2 lines in the same plane that never intersect. If you're wondering why this is necessary, Google skewed lines. S-K-E-W-E-D. Skewed lines. Perpendicular lines, they're lines that intersect. How do they intersect? At 90 degrees, right? A little extra information to make them perpendicular lines, not just intersecting lines. All right, let's kind of continue with our activity like we did with the widgets. Here on this slide, we have some examples of right angles, and we have some examples of not right angles. Think for a second and come up with a definition of a right angle. A right angle is an angle that measures 90 degrees. Here we have examples of acute angles on the left and not acute angles on the right. Take a second, see if you can come up with a definition of acute angle. An acute angle is an angle that measures less than 90 degrees. Obtuse angles on the left, not obtuse angles on the right. What's your definition? An obtuse angle is an angle that measures more than 90 degrees, but less than 180 degrees. A pair of complementary angles. On the left, we're being told that the measure of angle 1 plus the measure of angle 2 equals 90 degrees. And we're being shown here, angle 1 and angle 2 would add up to 90 degrees. And here, well, we have angle 3 and angle 4 adding up to 90 degrees. Therefore, both of those pairs of angles are complementary. On the right side, we're being told the measure of angle 1 and the measure of angle 2 added together does not equal 90 degrees. So we know that these two angles do not add up to 90 degrees, so they are not a pair of complementary angles. Angles 3 and 4 don't add up to 90 degrees, so they are not a pair of complementary angles. And angles G and H do not add up to 90 degrees, and therefore they are not a pair of complementary angles. So with all that information, what's a good definition of complementary angles? A pair of angles whose sum is 90 degrees. How about supplementary angles? On the left, we are told that the sum of the angles 3 and 4 is 180 degrees, and therefore they are supplementary angles. We can also see in this figure that angles 1 and 2 form a straight line, and therefore they must have a sum of 180 degrees, and thus are supplementary angles. On the right, well, angles 4 and 5 do not add up to 180 degrees, therefore they are not supplementary angles. And we see that angles 1, 2, and 3, all three together add up to 180 degrees. But that trio of angles is not supplementary. So what's your definition? A pair of angles whose sum is 180 degrees. Things get a little more difficult here with vertical angles. On the left side, you can see the three diagrams. We're being told that angles 1 and 2 are a pair of vertical angles. Angles 3 and 4 are a pair of vertical angles. And angle AED and angle BEC are a pair of vertical angles, as well as angle AEC and DEB. Those are vertical angles. Over on the right side, we have a bunch of examples of pairs of angles that are not vertical angles. So taking a very close look, what would your definition of a pair of vertical angles be? Angles formed by two intersecting lines. They share a common vertex, but not a common side. And our last definition, linear pair of angles. On the left side, we have examples of a linear pair of angles. On the right side, we have examples of not linear pairs of angles. Again, if you're watching this at home, pause the video, look at what we have, the information, and come up with your own definition. Two angles that share a vertex and a common side, and their non-common sides form a line. You can see the last couple definitions were a little more mathy. They were a little more technical. And being able to write a good definition and say what you mean is an extremely important skill, not just in math class, but in life.